Hello everyone, welcome to tutorial 1294. This is container networking from the shallow end to the diving pool. Thank you for joining me today. We're going to be covering 5 points in this talk. Just to let you know from a high level, what we're trying to do here is make sure that you are equipped to understand the terminology that you'll encounter in the networking portion of the Kubernetes world. Kubernetes obviously is an incredibly important product to SUSE. We're basing our entire container and application platform, the platform set on Kubernetes, and therefore we feel it's pretty critical to make sure that our customers, our field personnel, even engineering, product management, etc., are all educated into this particular area. So we'll be going through pods and containers. Those are some fundamental pieces of Kubernetes. We'll be drilling into namespaces and cgroups. These are 2 Linux concepts that really expose they make up pods and containers. We'll deal with some basic Kubernetes networking. We'll move into a primer in Cilium policy enforcement. Cilium is a CNI that SUSE ships with our CASB platform product that we feel very, very positive about. And then finally, a short conversation on service mesh. This talk was originally going to be a bit longer. We've cut it to 30 minutes in line with the rest of our SUSECON Digital delivery. And therefore, we will be shortening some pieces in this. Service mesh will be one of those pieces, so if you need more information on that, feel free to reach out to me. My email is at the start of the deck. Let's move on into defining pods and containers. Kubernetes networking fundamentally works on namespaces. Namespaces make up what are called pods in the Kubernetes world. Let's walk through a short example of how these work. In kernel space, in the Linux operating system of the node, there is a list of every single device running on your machine or attached to your machine. These include all network devices, disk devices, memory, processors, etc. So the kernel maintains a full list of those. Obviously, in the container world, you don't want every container to be able to see all of the device tables. There could be some devices in there that you want to keep hidden. So Kubernetes leverages namespaces in order to be able to filter some of those device names out. The way this works is whenever an open call is made or an enumeration call to list the devices, what happens is this namespace filter sitting in kernel space determines what the user space process is allowed to see. And it changes not only the total count of devices, it also changes the names of the devices according to how you would like them to be presented to this process. So in this case, we've taken /dev/en32, which is a standard Ethernet device name, and we've renamed it to ETH0, and we've hidden all other devices from this process. This is one of the fundamental things that makes containers work, and specifically networking within containers. Now, let's delve a little bit more into pods and containers. A pod is a Kubernetes construct around a set of namespaces. We will be drilling into that more momentarily, so I'm not going to go into that in depth right now. Just simply know you can't PS a pod like you can with a Unix process, because a pod is a set of namespaces that you can go ls, you can find them in the file system, but a pod is a Kubernetes construct. In addition, a container is a Linux process running inside a set of namespaces or a pod. So put simply, you've got Linux namespaces, you've got Linux processes, put those 2 together and you get containers and pods. Finally, Kubernetes will create 1 NIC in this pod's network namespace, and we'll go into the network namespace a little bit more here momentarily. 1 pod means you get 1 IP address. Now, you also have the concept of multi-container pods. A lot of workloads happen with 1 container running inside 1 pod, but at times you may have lots of processes running inside a pod, so you would have multi-container setups. Any container inside a pod can talk to any other container by talking on the localhost IP address. So any container inside a pod shares localhost. If one of these containers, by the way, let's say the one on the left was a web server and the one on the right was responsible for pulling content, say, from a weather site or from the stock markets. It was responsible for obtaining the data. The other one's responsible for displaying it and providing it to end users. The populator, the one on the right, would be called a sidecar. That's a term you'll run into. Just want to make sure that you're familiar with it. All right. Now, to make sure that you really understand some of the constraints or structures that namespaces and cgroups create for pods and containers, we're going to drill into those just a little bit more. So this page, or the content in this page, is from the namespaces man page inside Linux. So there are 8 at this point in time. These have been growing over time. It started off with a smaller number, but over time we find more and more cool things to expose and be able to constrain via namespaces. At this point in time there are 8. In the networking world for Kubernetes, the network and the UTS are the 2 relevant namespaces. And once again, we'll drill into those more momentarily. These others are very interesting and are also used by Kubernetes, but they're not necessarily applicable to today's talk, so I'm going to be skipping those for now. Let's run through some of those constraints, Kubernetes and namespaces. So Unix processes by default. When you kick off a process, it runs in the default namespace, which just happens to be in the Kubernetes world, the root namespace. A Kubernetes pod is a set of Linux namespaces. We talked about that a few moments ago, but now I really want to drive this point home. Think of a pod as a circle of 8 filters. That prior slide showed you 8 different namespaces. Every process will have those 8 namespaces, and you can isolate a process by creating a set of 8 namespaces specifically for it, or you can share potentially some of the default namespaces, and we will describe that here in a second. So Kubernetes will create those namespaces for each pod. That allows you to isolate these processes from each other. Here's where Kubernetes at times will share the root network namespace. If you're using Kubernetes host networking, all that means is that a process, a container in Kubernetes terminology, is running using the root network namespace. So there's a lot of mystery around host networking and people not being really clear on what that is. All it means is that process is running in the root network namespace and therefore can see all network devices, IP tables, the host routing tables, etc. It can see all of those that belong to the physical host or node. There's an asterisk there because there is a minor exception where if a network device has been removed from the host network namespace or the root network namespace and assigned to another namespace, you'll no longer be able to see that. But that's a rare event, and therefore it's apostrophed. Sorry, asterisked. All right. Cgroups. What are cgroups? This is the other half of the Linux structure that's used to really make Kubernetes work. Cgroups allow you to manage and report resource usage within your physical node. I've listed a subset of the items that Linux allows you to create cgroups on from, once again, the cgroups 7 Linux man page. I've pulled what I think is fairly relevant. It's important for you to be able to limit the amount of CPU, maybe create a minimum that's guaranteed to a process or a container, set a maximum that it can't consume above, and then be able to monitor the resource usage of a process. Because if you're doing, say, billing to a user that's running in your Kubernetes cluster, you'd like to be able to determine what they're actually consuming, not just what you may have allocated for them. And then obviously we can look at memory, disk I/O, network I/O, number of processes or containers you can create, and so forth. The real purpose behind cgroups inside Kubernetes is to be able to create, let's look at that bottom bullet point. It allows you to implement quotas or quality of service around those containers. All right, so that gives us an idea of what's going on within Linux itself in terms of how Kubernetes is leveraging these concepts. Let's now move up a level from the underlying Linux concepts and start drilling into basic Kubernetes networking. So Kubernetes networking rules, once again, asterisk down at the bottom. This is from the Kubernetes documentation. These 3 points are the critical, they are the truisms, if you will, that has to hold true across all different Kubernetes networking implementations, because there's more than one model you can follow, and we'll be explaining that further in the talk. But all Kubernetes networking models need to follow these rules. Now, if you really drill into these rules, you're going to see that NAT figures prominently throughout each one of these rules, and you can actually simplify these rules down into one, and that rule is as follows. Everything can see everything with no address translation going on. Now, address translation is an important piece of that statement. I want to make sure we unpack that for those of you who may not be crystal clear on NAT. And trust me, there's a lot more people in the world that aren't than may admit to that. So let's do a quick primer or refresher or a momentary rabbit hole into NAT. So everyone right now with coronavirus is obviously looking at working at home. This is a very good picture unless you are a freak and have your own internet routable addresses assigned to your office, and I'll admit to that. But very few people tend to be in that particular situation. The vast majority of people have an IP address that is assigned to them transparently to them by their ISP. It's assigned on their Wi-Fi router. On the right side, you'll see internet. All addresses on the internet are routable addresses. That means they're effectively the same as a valid phone number, a real phone number. Anything on the left side, this is supposed to show what your home might look like. You've got a couple of computers, a couple of cell phones that when you're home, you're actually talking on Wi-Fi rather than cell data. And then down at the bottom, you've got a smart TV that also talks via Wi-Fi or cabled Ethernet back into your Wi-Fi router. All of the addresses internally there tend to be non-routable addresses. So if you go do an IP config or something, IF config, whatever, on your particular device, you'll see an IP address most likely in a 192.168, a 10.00, or a 172.16 kind of range that is automatically assigned by that Wi-Fi router. Anytime you send a packet from one of these devices on the left to the internet, the Wi-Fi router translates. It hides your old IP addresses and it sticks its own IP address in. No one can talk directly in unless you have NAT rules, which we're not going to get into that. Okay? So this is what NAT looks like. Why does this matter? It matters for the following reasons. One, many, potentially most, Kubernetes clusters are set up with non-routable addresses. So they're set up inside a company network or inside a data center, and you don't assign official internet routable addresses to those. But here's the rub if you do that. Clients and users from the internet have to talk to services that are hosted by that cluster. So how do you make that happen? You add a piece of software that you've probably heard of in the Kubernetes space called an ingress engine. So this ingress engine allows you to translate from internet routable addresses to cluster non-routable addresses. So this should give you an idea when you hear ingress. This now gives you an idea on why ingress is important. Now, let's go ahead and drill into three basic Kubernetes networking models, and we'll be discussing, we've already discussed one of them, host networking, a little bit. We're going to be centering in on the final two. So if host network, the flag inside a startup file for Kubernetes is set to true, all pods will run in the root network namespace. This is efficient, meaning there's very little software overhead, but it's insecure. And many CIOs, security officers, et cetera, will have a problem with that. So a lot of organizations will say, nope, we're not going to turn on host networking. So that's why these other two models are potentially a little bit more important. The KubeNet model is what I would call kind of the default. It's a simple model. It's using a little bit of CNI, which we'll explain momentarily. Under the covers, it's more secure than host networking. That's a good thing. And then finally, there's a CNI model. And CNI is extremely powerful and flexible. SUSE supports this model as well. And there are quite a number of different CNI options or providers available. All right, let's take a look at Kubernetes networking using KubeNet, that middle model. If you are doing communication between pods on a single node, this particular picture is showing you two pods, a container inside each one, and they're talking to each other. How does the traffic flow happen? If the container on the left of your screen wants to talk to the container on the right, it will send traffic out through its network interface, which happens to be in Linux words called a vEth. This is the equivalent of a pipe, okay? So all traffic goes through that vEth inside the own namespace of that pod and container, and now you will land on a Linux bridge. This Linux bridge is running in user space in the root net namespace. This is effectively a software emulated switch. So imagine a Cisco or a Brocade or a Juniper or a Arista switch. It's basically taking the code out of that and sticking it inside a Linux process inside user space. It's really powerful, but it's a little slower than you might like. KubeNet is not built to be extremely high performance. It's built to be simple and functional, okay? And then once Linux Bridge has determined that traffic is now bound for the second pod, it does a mem copy out through the vEth pair back into the other pod's network namespace. There's context switches along the way from user to kernel space, and then finally the traffic lands in that other pod. This is how intranode pod-to-pod communication occurs. Here's an example of internode pod-to-pod. Only thing that changes, we basically doubled the number of nodes because we have to add a second node if we're going to have inter-pod communication. And then we have traffic transitioning across a physical Ethernet between these two boxes. So very similar, just one more layer of indirection across a physical link. Here's the emphasis, and I've mentioned this before, but this is a critical point for you to use, and it actually will come up as we discuss policy enforcement momentarily. The primary policy of Kubernetes networking is hiding complexity, making it easy for developers to end up working with this, and enabling everything to see everything else with no user effort. And a little footnote there, this is a far easier model than what Docker was. That's one of the things that caused Docker some difficulty in the market, was getting all of its networking models to work was actually quite a bit more difficult than this. All right, one more quick example. I want to drive home the point that different CNIs may implement their underlying network models a little bit differently. This is one of the Docker container runtimes running inside Kubernetes. You see some mild differences, maybe some additional IP address changes that happen, but other than that, the overall functionality is the same. Container 1 on the leftmost host can communicate with, say, container 2 on the rightmost host by flipping up through the Docker 0 bridge, ETH0 through the router gateway, and then back down the other side. Now, I want to talk about the third model that we discussed, the networking model that we discussed Kubernetes supporting, and that is a CNI model. A CNI is a container network interface. It allows you to add network-specific functionality into Kubernetes in an extensible and consistent manner so that it's not the wild, wild west in terms of development. People are following the same kind of mechanisms and structures for adding that functionality. So let's delve real quickly into what Cilium is. This, by the way, is a technology that SUSE has been shipping for a while with its CAS platform. As I delve deeper into this, I think you're going to see why SUSE is so excited about this and why we think it very strongly meets our customers' needs. So first of all, let's kind of do an architecture on how Cilium, Kubernetes, and these other technologies all fit together. So for me, easiest way to look at this one, and maybe I did this slide or built this slide a little bit before mealtime, so I used a sandwich analogy. So Kubernetes, this is our tool and our primary view of the world. When you're eating your sandwich, you're looking down on that top piece of bread. So that's your view of the world into this network stack. Now on the bottom side, you've got kernel capabilities, much like namespaces and cgroups, but in the equivalent network functionality. So in that networking functionality, the two pieces that are critical to us there are Berkeley Packet Filter, more commonly called BPF, and then XDP. Now BPF has been around for a very long time. It was a BSD technology that's been added into Linux. It's very high performance and stable inside Linux. Excellent piece of kit. XDP is a network-specific Linux kernel layer technology. It allows you to accelerate some network functionality. And the way that Cilium works, it uses both BPF and XDP. So BPF and XDP, the bottom layers of this, are the bottom bit of bread holding your sandwich up. Cilium, it's the meat in the middle. It translates from these Kubernetes networking constructs to BPF and XDP. So Cilium is very much a Kubernetes-specific representation or exploitation of BPF and XDP, which is the bottom layer of the stack. All right, let's take a look at a picture. How does this actually implement compared to the kubenet and the Docker structures that we just looked at momentarily, just a couple of moments ago? So you have a node, you have two pods. So this is our intra-node pod-to-pod communication. First thing that you see is the pods, containers, and VETHs for the two pods all look the same. We've added an additional piece, which is a little BGP circle. This is a BGP program running in user space. BGP is a routing protocol, and it watches packets go by or can be configured to say, I want the following stuff to go this particular direction. So extremely, extremely useful, excellent routing protocol. It speaks to a routing table inside the kernel. In addition, there are BPF programs. We mentioned BPF in the last slide. So what happens is, if a pod needs to talk to another pod, it will send data out its VETH. You'll notice this does not go into a Linux bridge now. It does not go back up into user space. So we've eliminated a context switch, which is a major savings, because the other side doesn't necessarily have that context switch either. We may have eliminated multiple context switches. When a packet lands from pod 1 into the kernel space, BPF programs execute. These are filters. They allow you to filter packet traffic and say, hey, I want the following kind of packets to go here. I want you to drop these other packets. I want you to edit other packet types as they go by, and so forth. BPF is an extremely efficient technology. It's tuned for packet filtering. So you'll notice on that third bullet point on the right where we say no IP tables replaced with BPF, the default for Kubernetes is IP tables. This requires multiple mem copies, creating structures called SK buffs, moving data into them, editing those data in place, potentially copying them into another buffer, etc. A lot of overhead. BPF eliminates all of that. So that final bullet point, between BPF not requiring IP tables and XDP allowing you to completely bypass SK buff, this is a set of the reasons why BPF and therefore Cilium within a Kubernetes construct is so incredibly efficient. This is one of the things that excites SUSE. In addition, BPF programs are highly extensible. We're actually seeing a lot of activity right now in the market attempting to, or working at moving BPF capabilities into, say, the application security environment. So instead of something like AppArmor or SE Linux, SE Linux specifically is an extremely heavyweight, unwieldy architecture, in our opinion. AppArmor a little bit lighter weight, whereas BPF is extremely high performance, very malleable, and quite secure in and of itself. So once again, we're really excited about this technology. Now, that's the tool, that's the architecture. Now let's talk about what we actually do with it inside Kubernetes. Why do we need this? So let's do a bit of a rewind. Remember that all pods can see each other. If everything can see everyone else, what about security? Second bullet point, and this, remember that Kubernetes, a lot of that came out of the Google ecosystem. Developers love the Kubernetes networking model because they don't have to mess with the networking. It just works for them. But on to the next bullet point. Security officers, IT managers, and CIOs would like to see something a little more in the way of security. So thus, in the Kubernetes world, the concept of policy enforcement was created. We want to limit who can see what. So we want to have the best of both worlds. And honestly, I think Kubernetes has done quite a stellar job of this. You want to have the base, get it started, everything can see everyone, and then over time, as you want to start limiting who can see what, as you move this into production and want to keep things secure, you want a very easy, scalable, and fast, as I put it in the last bullet point, you want an agile, cloud-native DevOps kind of way of getting that policy enforcement put in place. How do you do that? Very, very simply. On the left side, and if anyone's interested, I did not get the URL for this talk in here, you can just search for CNCF webinar on Isovalent and SUSE. This slide is actually taken from a talk that the president of Isovalent and myself did for CNCF a while back on this technology. So feel free to look there. If you can't find that, once again, reach out. On the left, this is a policy declaration for what you want Cilium to enforce. All this is saying is, look, I want anything that's labeled as a backend on Kubernetes, so maybe a database, to be able to accept traffic from anything that's labeled as a front end inside my cluster. That front end might be a web server. This one statement is created once, you type it in, hit enter, and what happens is it gets applied to every node in your network. As new pods come online, as maybe your web server scales out, that policy will automatically be applied there. It's really fast, really easy. I have the historical view on the right. If you're going to do IP tables rules, these rules are the kinds of things that you manually type in each time, and you fill in the bash variables, the dollar bracket constructs with the IPs of the additional pods that you want to do. One is high overhead, one is extremely simple and automated. Now, I'm going to give a quick shout out to SDN. I've spent quite a bit of time in the SDN marketplace, specifically around the OpenStack market. SDN is software-defined networking. There are actually multiple definitions of this. Each network hardware vendor, commercial and open source vendor, and even analysts tend to have their own definitions of SDN. What happened is I worked through a lot of those definitions and tried to come up with what is my favorite definition, which just happens to be the one that I created, and that is, very simply, SDN provides the ability to, from a central spot, manage and deploy network policy to different types of network devices. So in the virtualization world, you can have different types of network switches, you can have different virtualized hosts that maybe have OVSs or Linux bridges or a vSphere network switch, etc. And you can have that policy pushed everywhere from one click. All of that can go out, so you don't have to be an expert in every single technology inside your organization. If you look at what Cilium is doing here, it provides the ability to centrally manage and deploy network policy inside your Kubernetes cluster, regardless of how many nodes come online, how many additional workloads are dynamically created or scaled out, etc. So you'll notice that it provides a very similar type of functionality in the Kubernetes world to what SDN provided in the virtualization world. So it actually addresses a problem that SDN may not match quite as well to the Kubernetes world as it did to the OpenStack world, but the functionality still exists, just in a little bit of a different incarnation. All right, finally, let's wrap up with a little bit of service mesh. And once again, because this was a 30-minute talk, I was able to cover the wading pool, the 3-foot section and so forth. The diving pool or the high dive may need to wait for another talk. So we will do our best to construct one of those for you and make sure that you have a solid resource for service mesh discussions from SUSE. But what I am going to do is I'm going to give you a little bit of a talk about why service mesh is important, why it matters, and I'm going to use one use case within service mesh. So what you see in front of you is a slide that I think we first presented at Nashville, Tennessee, last year's SUSECON. This was an NFV talk. We were talking about, look, what's really happening in the market that people have to go through in order to move from their historical environment, which are telco appliances, into a cloud native or a mode 2 or a 12-factor type application, which is what you see in the rightmost column. So on the left, telcos currently buy appliances. They're almost always x64 based, sometimes ARM based, often Linux-based. They'll have ASICs and FPGAs, accelerated silicon, if you will, and the applications are stateful, monolithic, and long-running. They have to have 5 to 6 nines of time worth of uptime. As people are beginning to virtualize these appliances are expensive. There's large profit margin built into these. There's a large cost structure as well in those appliances, but telcos want to cut that margin out so that they can deliver more cost effectively. So they're very interested in this middle section, and this is where many of them are or are moving strongly today. This is a mode 1 application. It's either a virtual machine, it's a virtual machine generally, so an application sitting inside a virtual machine. What's happened is the engineers for this have picked the code up out of this appliance and they've plunked it down in this green M1 bubble. What's the blue database icon? That's the state. Here's the problem. Many users may hook up to this M1 and their state is going to be contained in that M1. If this M1 or virtual machine or the node hosting the virtual machine dies, all that state goes away. This is a bad thing. This is why, and your phone conversation, your cell phone hangs up on you. That's what happens whenever this type of application dies in a network data center. That's why telcos want to move to this M2 or stateless model. So what happens is in order to move from this M1 to M2, you literally have to rewrite the software. Almost never is an M1 written to where it can be very easily taken apart and just start up multiple copies with one per user. So there's a little bit of a deconstruct that has to happen in a re-engineering, and that's why that first bullet point under Mode 2 application says this is a redesigned code base. But now it's stateless. You'll notice the database has moved outside. It scales out. Think about this M1. This M1 actually can consume an entire physical machine, even if it's sitting in a VM. But if that physical machine or VM can't scale up, you've reached the limit of your scalability. With M2s, you can start throwing them at nodes all around the network, all across your Kubernetes cluster. So this is extremely scalable in a scale-out architecture. This is work that telcos are doing right now in conjunction with their ISVs and with Kubernetes vendors like SUSE in order to move into this market. It's going to take some time to do, but trust me, this work is going on right now. What impact does this have? Why does this matter to service mesh? Like I said, I'm going to drill into one point. If you look at all those M2s, there are many endpoints. They all expose a single service. The question is, if you're outside this cluster and you need to talk to one of those, which one do you talk to? They may have different IP addresses and different TCP ports. So that third point really stresses that along with the non-routable addresses, all of those IP addresses and ports are ugly and difficult to type into a browser. You need a service that allows you to consolidate all of those and basically hide them behind a single viewpoint like a load balancer or an Ingress server that says, hey, type in this one URL, which is very easy to type in. We'll take care of the dirty work and figure out which one to map you to behind the scenes. So Ingress is just one benefit provided by Service Mesh. Like I said, we're out of time for this talk, so look for more information in the follow talk coming to SUSECA's platform soon. That brings us to the end of our session. Thank you very much for joining us. I hope you enjoy the rest of your day.